Hi, welcome to Collins Chemistry, Episode 3, Thermochemistry, or more specifically, specific heat calculations. Specific heat is defined as the amount of heat needed to enter or leave a mass of a substance in order for that substance to raise or lower its temperature by 1 degree Celsius. A substance with a high specific heat is very resistant to temperature change. For example, liquid water has a high specific heat of 4.18 joules per gram degree Celsius. That means that liquid water can be used as a coolant in car engines and in nuclear power plants. On the other hand, metals have very low specific heats, which means they heat up and cool off extremely quickly. Have you ever tried to go down a metal slide? I know I'm dating myself, that's old school here, but have you ever tried to go down a metal slide in the sun and you can't put your legs on it because it's really hot? That's because metal has a low specific heat. Let's get to some calculations now. You are freezing water with a mass of 3.50 grams from 0 degrees Celsius to -7 degrees Celsius. How much heat is lost in this process? We are going to start with the equation Q equals mc delta T, where Q stands for the heat, m stands for the mass, in this case the mass of the water, C stands for the specific heat of the substance, and delta T stands for the change in temperature. This little triangle here is the capital Greek letter delta, which means change in. So delta T would mean change in temperature. So let's fill in our numbers. So Q is the heat, and I'm being asked in this question how much heat is lost in the process. So I don't know what Q is yet. That is what I'm solving for. So I'm going to put a big question mark with the Q. M stands for the mass. In this case, the mass of the water, which is 3.50 grams. C is the specific heat. The specific heat of solid water is actually lower than the specific heat of liquid water, which I referenced earlier. The specific heat of solid water is about 2.06, and the units for specific heat are joules per gram degree Celsius. They can also be in calories per gram degree Celsius, but we're going to stick with joules for now. And the change in temperature, I wasn't given an actual change in temperature, but I was given two different temperatures. So with the two different temperatures, I can calculate the change in temperature by subtracting T2, the second temperature, minus T1, the first temperature, or T final minus T initial. In this case, T final is -7 degrees Celsius, and my T initial, or my T1, is 0 degrees Celsius. So -7 minus 0 is -7, and that gives me a delta T, or a change in temperature, of -7 degrees Celsius. So now I can take these numbers and just plug them into my equation and chug the math. I call it plug and chug. So I have Q equals, M is 3.50 grams times C, 2.06 joules per gram degrees Celsius, times delta T, which is -7 degrees Celsius. Now I can cancel some units here. So, for example, I have grams on top here, grams on the bottom here. Those can cancel. I have degrees Celsius on the bottom here and degrees Celsius on the top here. Those can cancel. And I am left with joules. So when I multiply all of this out, I get Q equals -50.40 joules. Now notice my Q is negative. That means this is an exothermic reaction. It is giving off heat. It is losing heat. So if this is an exothermic reaction that is losing heat, my Q is going to be negative. On the flip side, if my reaction were actually gaining heat, Q would be positive. That would be an endothermic reaction. All right, let's try another example. You are smelting iron to make steel. If you add 19,028 joules of heat to heat the iron from 30 degrees Celsius to 1,538 degrees Celsius, how much iron can you smelt? Again, we are going to use the equation Q equals mc delta T. So Q is our heat, and in this case that is given to us. That is 19,028 joules. So I'm going to write that down for my Q. Mass. That is what I do not know. So I need to find out my mass. It says how much iron can I smelt? The specific heat of iron is 0.444 joules per gram degrees Celsius. And I just got that online. There are plenty of tables online, plenty of places you can look it up online. You can look up the specific heat of just about anything online. So this is 0.444, and again the units for specific heat are joules per gram degrees Celsius. And my delta T, again, I wasn't given a specific change in temperature, but I can figure it out. I have my T final minus T initial, which is 1,538 degrees Celsius minus 30 degrees Celsius, which is going to give me 1,508 degrees Celsius for my delta T. So now, if you notice, M is what I'm solving for, and it's not on the left-hand side of the equation by itself. I can do this one of two ways. I can either just plug in all the numbers and check the math, or I can get M by itself first, then plug in all the numbers and check the math. So I'm going to do this both ways. First, I'm going to get M by itself. So in order to get M by itself, I need to divide both sides by C delta T. And when I do that, I get M equals Q over C delta T. So I can plug in my numbers. M equals, Q is 19,028 joules over C is 0.444 joules per gram degrees Celsius times my delta T, which is 1,508 degrees Celsius. So now I can cancel some units. I have joules on the top of a fraction here, joules on the bottom of a fraction here. Those cancel out. I have degrees Celsius on the bottom of a fraction here, and degrees Celsius on the top of a fraction here. So those cancel out, and I'm left with grams. So when I do that, I get my mass equals 28.42 grams of iron that I can smelt using that amount of heat. Conversely, and I'm going to run out of room here, conversely, I can just plug in the numbers and get 19,028 joules equals M times C, 0.444 joules per gram degrees Celsius, times delta T, which is 1,508 degrees Celsius. And when I chug that math, I get the same thing, 28.42 grams of iron. All right, let's do one more example. You are a glassblower who just blew 15 grams of glass into the shape of a cup. While cooling, this cup loses 1,261 joules of heat. what is the change in temperature? So let's plug in our numbers again. Remember, Q is the heat, M is the mass, C is the specific heat, and delta T is the change in temperature. So my heat is 1,261 joules. My mass is 15.0 grams. The specific heat of glass is 0.840 joules per gram degree Celsius, and again, I just looked that up online. So 0.840 joules per gram degree Celsius. And delta T, my change in temperature, that's what I'm solving for. So now I can just plug in my numbers, or I could get delta T by itself first and then plug in my numbers. So let's do that method first. Let's divide both sides by mass times specific heat. And I get delta T equals Q over mass times specific heat. Now I can plug in my numbers. So delta T equals, my Q is 1,261 joules, over my mass is 15.0 grams, times specific heat, 0.840 joules per gram degree Celsius. And again, I can cancel my joules, I can cancel my grams, and I'm left with degrees Celsius. And when I do that math, I get delta T equals 100.1 degrees Celsius. Now, the other way to do it is to just plug in the numbers immediately. So I get 1,261 joules equals 15.0 grams times 0.840 joules per gram degree Celsius times delta T. And when I solve that math, once again, I get 100.1 degrees Celsius is my delta T. Now let's take this one step further. So, if my initial temp was 930 degrees Celsius, what is my final temperature? Now remember, we are cooling, so the system is losing heat. That makes it exothermic. If the system is losing heat, I am going to take my initial temperature, 930 degrees Celsius, and I am going to subtract my change in temperature to get my final temperature. So, T initial minus delta T is going to get me my final temperature. So I have 930 degrees Celsius minus, and my delta T was 100.1 degrees Celsius, and that's going to leave me 829.9 degrees Celsius is my final temperature. I hope this was helpful. If you have any questions, leave them in the comments, and best of luck. Thank you.